So hey guys, my name is Nikita, and I'm a software engineer for Rival Hive here in the Los Angeles office. A few weeks ago, Matt gave a presentation on what is Hive. So just to summarize, Hive is a Los Angeles-based team with the aim to build a democratized vehicle simulation platform. You might remember this slide from his presentation, where he talked about all the different use cases the Hive framework aims to facilitate. We want this framework to be used for a variety of different simulation tasks, stuff like engineering simulations, racing sims, and very importantly, training autonomous driving systems. So today I'm going to talk about a software framework. Um, Building a vehicle simulation platform inherently implies fast inner loops and low latency. However, the challenge we have is that facilitating all these use cases also requires the platform to be very scalable and flexible. So on this performance or scalability graph, we really have to try to push up both axes at the same time. So let's talk about how we're doing that with our framework. So on this graph here that Matt showed you previously a couple of weeks ago, we have the graph architecture in the middle, the pub sub-architecture in the bottom right, and in the top left, we have the more sort of like integrated solution. Well, I'm going to tell you guys about another design pattern called ECS. ECS is a type of data-oriented approach to development, and it's commonly used by game engines for its performance benefits. The general idea is that by being data-oriented, you write your programs around your data instead of trying to shoehorn your data into your program. This allows you to be more clever with the way the data is laid out in cache memory, which can yield substantial performance improvements. And this puts it on par with sort of the best case scenario integrated solution, while at the same time being more scalable. And now the approach we took here at Hive is a little bit different from a traditional ECS. It's what we call a DECS or duck ECS, which stands for duck type ECS. Basically, the difference is that we made the way the program accesses the data a lot more flexible, which without sacrificing any performance, moves our architecture to the right along the scalability axis. So the next thing we did was we took the systems, which is the S in ECS, and we made those systems be component-oriented. Component-oriented programming is yet another design pattern that aims to split your program into reusable modular chunks. So by making the systems be these modular components, we yet again made our framework more flexible and scalable, which moves us to the right again. So to sum up, we took an ECS, we added duck typing to it, and we made the systems be component-oriented. Now you may have noticed that we haven't really moved up much. We basically just took the ECS architecture, which is already highly performant, and we moved it to the right by making it much more flexible. So I have a few videos lined up to kind of show off the cool kind of stuff we can do with this flexibility. So this video is a demonstration of a concept called hot reload. So if you remember those component-oriented systems I mentioned, well, because they are component-oriented, we can actually swap them out during the runtime. So in this particular example, we have a test component where right now all it does is returns a string, and that string is being displayed here over the car. Maybe hard to see because it's a bit pixelated, but that's this test right there. And basically what I can do is I can just go in, I can change the code and change the implementation of this component, which in this example I'm going to do just by changing the return output of the string. And then I can recompile the code. And once it's done recompiling, you will see it get hot reloaded and update. And I'm just going to skip forward here a little bit because it takes a while to compile right now. But yeah, you're going to see it finishes compiling, and then boom, just like magic, it swapped out the implementation of the component it was using in real time. And this is a really useful thing to have when you're developing a vehicle sim, because it allows you to feel the effects that your code changes have to the behavior of the sim, like immediately in real time. And this is a bit more of an advanced example of the creative kind of stuff you can do with these systems. So a few months ago, I was debugging some jitter and suspension solve. So as a test, I just ran a simulation with 2 different rigid body system implementations that were being stepped side by side. And this kind of made it really, really easy to spot the difference. And being data-driven, it makes it a lot easier to do distributed computing. Since the data is more clearly defined, we can just share parts of the data system across the network using what we call a Hive host. So in this particular example, if you notice those 2 camera views at the bottom, those are actually being rendered on a different machine in real time and streamed over the network. And that's the only reason why this demo can run at a reasonable FPS. If you tried to render those camera views on the same machine, you'd get like 10 frames per second. So now I'm going to pass you guys off to Saul, who's going to tell you a little bit more about Hive Host and how we can leverage the component system to do different, more kinds of cool stuff.
Right. Thank you, Nikita. So hi, my name is Saul Rodriguez, and I'm also a member of the Hive Arrival R&D team. Using the slide that you are becoming more familiar with and that emphasizes one aspect of our engine, mainly its plugin side, I will be sharing 2 demos. The first demo, we will see 2 distinct vehicle physics models, one developed by our colleagues in St. Petersburg and another developed here in Los Angeles in preparation for our high fidelity model using the DEX system that Nikita just spoke about. You will see 2 ADS drivers, one developed by RoboRace and another developed here in Hive. One of the vehicle models is run completely in Unreal using the NVIDIA's physics engine, while the other is run entirely on a separate process within the Hive engine. And being a plugin architecture, we could easily have used a different render like Unity or Godot, or our own render called Model View. And finally, our own Hive host is instantiated in 2 separate processes. The first one is purely Hive, which runs 100% of our vehicle simulation, including the tire to surface collisions. And the second process is in Unreal to manage different components of each vehicle, like the Hive vehicle movement, and also the CAN modules that are used by the St. Petersburg vehicle model. So on this video, you see 2 vehicles. The one going ahead is the one developed by St. Petersburg. And the one on the back, the dark, is the one developed by Hive. And the 2 simulations are running different processes, and we just used Unreal to render both vehicles. So the Hive engine has complete knowledge of the surface, and it's doing the entirety of the simulation, including the, as I said, the surface to road collisions. Okay. In the second demo, we also reiterate the plugin architecture. We go more on the scalability. And we have 4 vehicles with 4 different drivers, a human driver and 3 ADS drivers with different personalities that we call timid, aggressive, and reckless. We also display 2 variations of our vehicle model, which are free body and curvature threshold. And we have 2 vehicle specs, one being the DevBot and the RoboCar, the second. And last, instead of using Unreal, we use our model view, which uses OpenGL and also has options to use Pixar's Hydra rendering technology. So here it is. The orange vehicle is the human driver. The darker blue is the reckless ADS driver. The purple going ahead is the timid driver, the timid ADS drivers, and the light blue is the aggressive ADS driver. So as you see them, as this video progresses, you will see that the reckless starts to go ahead because it has less consideration for slippage in the road. All right, so this is the Hive engine, and I'm happy to take any questions. Thank you very much for your attention.